But perhaps where I really disagree with Sabine is her statement that the Standard Model is complete. There's two aspects to particle physics. There's the particles, and the set of particles is complete. And there's the interactions. And the interactions are nowhere near complete.
Well, a particle it's an irreducible representation of the Poincare group. So I think that the way that I think about those questions, what is this or what is that, is what's the mathematics that we use to describe this thing? And we understand this very well. So we use certain types of mathematical operators and certain types of spaces. Then we have this thing that we call quantum field theory, and it's really complicated with all kinds of operators and so on. And we have that part done.
Well, it's always dangerous to say you're done.
Are we right to continue searching for ultimate particles in the way we have done for the past 50 years? And I'm going to put that to Sabine first.
Oh, I get to go first. All right. So I think my answer to the question is no. Okay, so I guess I should expand a little. So for the past 50 years, we've had good reasons to think that we haven't yet found all the fundamental particles of nature. So we've had this thing called the Standard Model, and we have had certain theoretical expectations of what should be in that model, what kind of particles, how many of them, what should their properties be. And over the course of time, we filled in the model. So we found them all. The last particle to be found was the Higgs boson, which was found at the Large Hadron Collider in 2012. And with that, the Standard Model of particle physics is complete. Now, theoretical physicists have some misgivings about that Standard Model. They basically think it's not pretty enough. And this is why they've proposed that there should be other particles, because then it would be prettier. I don't think that's a particularly good motivation to keep on looking for new particles. And so I think at this moment in time, particle physics is in a good shape. You know, it works well. The Standard Model describes all our observations in particle physics. But we have other things to worry about, notably in astrophysics, where we have these things, dark matter, dark energy. There's some things we don't understand about the expansion of the universe. We have some issues with quantum mechanics and so on. So those are all areas where we are doing and should be doing experiments to push the boundaries, to learn more about the foundations of physics. But at this particular moment in time, I think investing more into particle physics is not the right thing to do.
Thank you, Sabine. Gavin, I'm going to go to you next.
Okay. So Sabine and I are sitting at opposite ends of this panel, unsurprisingly, because we have opposite views. A good sort of two swords length between us. So unsurprisingly, I'm going to say I think we should carry on. I think the only way we have of understanding and probing and exploring whether there are new particles is by building colliders and running those colliders. But perhaps where I really disagree with Sabine is her statement that the Standard Model is complete. There's two aspects to particle physics. There's the particles, and the set of particles is complete. And there's the interactions. And the interactions are nowhere near complete. In fact, one of the mysteries of the Standard Model of particle physics is that all around us there's a field. Fields, that's physics talk. What is a field? Well, a magnetic field is something everyone knows about. You've got a compass, you can sort of detect that magnetic field. And we know what causes that magnetic field. It's because there's a big magnet in the middle of the Earth. Well, all around us there's another field. It's the Higgs field. And that Higgs field has a much, much bigger impact on us than the magnetic field of the Earth. Or rather, the Standard Model says it does, but there's not a shred of evidence for why the field has the value that the Standard Model says it does, and there's not a shred of evidence for it actually having the impact on us that the Standard Model says it does. For example, it gives the electron its mass. Now, electron mass is 0.05% of our mass. You might think, who cares about that? But 0.05% of mass actually sets the size of atoms. And if it were half of that mass, if the electron mass were different, we'd be twice our size. And supposedly that comes because the electron interacts with the Higgs field. That's a hypothesis. It's not been tested. And so there are a whole set of questions out there that particle physics actually could answer in the next 70 or 100 years. We're thinking big time scales. It's not easy. But we think that particle physics could get there and actually would really shed light on the world around us or definitively rule out the Standard Model.
Okay, so I'm getting a distinction between knowing about particles and knowing about fields. But Sabine, do we actually know what particles are? Have we got that established, in your opinion?
Well, I'd say particle physicists know pretty well what particles are. I mean, they have that going for them. Though I have to say, I read the description of this debate and I came across the question, what is a particle? And I have to admit that when I would have to answer this question, I'd say, well, a particle it's an irreducible representation of the Poincare group. But I'm afraid most people wouldn't know what this means or what to do with it. So I think that the way that I think about those questions, what is this or what is that, is what's the mathematics that we use to describe this thing? And we understand this very well. So we use certain types of mathematical operators and certain types of spaces. Then we have this thing that we call quantum field theory, and it's really complicated with all kinds of operators and so on. And we have that part done. And so I'm not sure that science can even answer the question beyond that. Like, what could possibly answer the question, what a particle is, beyond this mathematical construct that we use to describe it? I don't know.
So then does the Standard Model represent reality then?
It describes it. Does it represent it? I don't know. It's the best we can do.
Gavin, what's your view?
I'm actually pretty much on the same wavelength as Sabine here.
Oh. You can move your chairs together.
At the end of the day, you've got a description and you've got data. You can go and do an experiment and collect data. And you ask, do they agree, do they not agree? And if they agree, you're doing a good job. Now you can try and ask about the philosophy that's behind the description, and sometimes you can get your head pretty tangled up. But if that tangle doesn't predict anything different about what the data is going to look like, that tangle at some level is metaphysical rather than scientific. And so far, it predicts everything extremely well. So there's not really an issue there.
So are we continuing the search for ultimate particles, or are we done? We found everything there is to find?
Well, it's always dangerous to say you're done. Historically, when people thought they were done, they probed further and they found actually they weren't done at all. For example, they found that protons and neutrons had stuff inside them. They had a size. They had constituents. You never really know the answer to that question. And that's part of where the difficulty and the disagreement maybe is. Because when do you stop? If you don't know if you're done, when do you stop? Do you always just carry on going further and further and further? And if you find nothing, and you carry on finding nothing, and you carry on finding nothing, do you stop? And that question of finding nothing is, in a sense, one of the elements of where we disagree, because we haven't found any new particles since the Higgs boson was discovered. But we have found interactions that we'd never looked at before. And I would say we're actually finding stuff, and we've made major discoveries over the past 5 years, and there's major discoveries still to come. So in that sense, there's definitely a future. There's definitely something that you can target, that you can hope to reach, as opposed to the ultimate particle where you don't know what the target is, you don't know if you'll reach it.
So is that what we're discussing then? That we have found a particle like the Higgs boson, we haven't found anything of significance since, and so are we at some kind of fork in the road in our approach?
Well, it's a little unfair, I think, to say we haven't found anything of significance since the Higgs boson. Yeah, so first of all, let me say that I agree with what Gavin said that we never know that we're done. And I didn't mean to raise the impression that we're sure there's nothing more. Of course, we don't know. It might be that there are more particles. For example, we have the stuff that we call dark matter that we don't really know what it's made of. And a lot of physicists think that it's actually made of particles, which raises the question, well, how could we find out? So you can try to produce those particles, for which you could use a really big particle collider, or you can try to measure the ones that go through our planet, and there are experiments running that have been looking for those since the 1980s. The problem is they haven't found any. And this raises the question, like, how long are you going to continue with this kind of thing until you give up? And I've come to the conclusion that this just isn't a particularly useful strategy to keep poking around in the dark, building detectors, hoping that the kind of particle that you believe exists turns up in this detector. It's just not working. And when it comes to building bigger colliders, it's true, of course, you build a bigger collider, you can make more precise measurements. You can learn things that are interesting for particle physicists, like properties about the Higgs field, how it interacts with fermions, whatever. And it's true, there are things that we haven't measured before, and I'm not saying they're uninteresting, but it's not like we make a fundamental breakthrough by measuring those things. And this is why I think that at this present moment, there are just better things that we could be doing in the foundations of physics. And so particle physics at this point in time is not a particularly hot research area.
Gavin, what do you say to that?
So one of the dangers in science is having a blind spot. And I think there's a problem that the field has a blind spot, which is this assumption that just because you've looked at the standard model over and over again, and it seems to have worked, that the whole of the thing is right. And the bit we've looked at is the bit that's like electromagnetism. Basically, the standard model has electromagnetism in all sorts of variants, and we've tested that bit over and over again. But the whole thing rests on a completely different structure. And that other structure, which is connected to the Higgs, actually, we're only just barely starting to probe. So it's pretty fundamental. In fact, it's arguably it's the keystone of the whole standard model. So to say that we don't need to look at it just because things have worked so far, I think is really sort of a dereliction of duty for a physicist. It also ties in many ways with fundamental questions, like dark energy. We don't know. The universe is expanding faster and faster, but only very, very slightly. And when you look at the standard model, without really adjusting it very finely, you'd have a completely different properties of the universe. And they're connected with this Higgs field. And what we cannot do is actually figure out whether the Higgs field is what is driving this or not, or how it's connected with that. But when you know that there's a problem, that you're basically almost a brutal inconsistency in your theory, then you better go and check that theory in more detail. And that's the attitude that I take with respect to this.
Sabine, would building new accelerators be worth the cost?
Well, I don't think so. But before I make my point, maybe I should clarify, it's not that I don't think anyone in physics thinks that the standard model is the last word. We do have good reasons to think that there's more than the standard model. Like, for example, there's some issues with the neutrinos. There are issues with the quantization of gravity. There are issues, at least I would say, with the measurement problem in quantum mechanics and so on. It's just that building bigger colliders isn't going to do anything about those issues. And also dark energy, I don't think you'd learn anything from a bigger collider about dark energy unless you get very, very, very lucky. It's possible, but I find it very unlikely because it's really a cosmological thing. And yes, there are some ideas that it has something to do with the Higgs boson, but it's not generally accepted thing. And this is why I think if we want to make headway on those problems that we want to know an answer to, like what is dark matter, what is dark energy, what's with the measurement problem, quantum gravity and so on. There are better experiments that we could do. So I think that the smart thing to do at this time is to invest the money into those experiments where we have a fair chance to actually find something new, and that would help the theory development. And then we can try to decide, like, is it now worth building a bigger collider to test some of these things? Like, for example, you might be looking out into the cosmos and actually figure out where dark matter has to be made of some kind of particle which has this and that energy and this and that interaction. And then we know what's the kind of detector or the kind of machine to build to investigate that kind of thing. But at the moment, we're not in that position.
It's true, Gavin. For a while, I mean, we'd never found dark matter. We don't know what it is. None of the experiments built have found any answers.
That's quite true. In fact, we've known about dark matter for maybe 90 years, and people have looked for it and looked and looked. But colliders were never guaranteed to find dark matter. That's not what you build them for.
Why do you build them?
You build them because you want to explore new energy domains. You might get lucky, and it might turn out that in the energy domain you're exploring, a dark matter dark matter candidate pops out. But you would never actually know if it was a dark matter particle or not. You'd know that it's a long-lived particle. Long-lived on a detector scale, it means 10 nanoseconds. Dark matter has to live the age of the universe to be dark matter. Now, that's not to say that some of my colleagues didn't say we would find dark matter colliders. Quite a few did. People got carried away. Scientists get carried away like everyone gets carried away. But there were some of us who were actually saying, no, hang on, that argument is a delicate one. That's not why we're building the collider. We might get lucky and find dark matter, but we're building the collider, we're running the collider just to search generically, to search for all sorts of things, searching for thousands of different kinds of things to see if they're out there. And that's the nature of science. You have to explore at some point. If you stop exploring, you stop looking, going places you've never been before, you effectively stop doing science. Now, the disagreement is, where do you go looking? And what I'm saying is that, well, build a new collider, go and look generically at sort of significantly higher energy scales. And at the same time, you know that that collider is going to tell you something about the Standard Model. You've got a guaranteed discovery as well as the possibility of exploration.
Did you say build a new collider?
Yeah.
So you're in agreement?
Well, no, because Sabine says we should not build a new collider. It's a waste of money, to paraphrase her. And I'm saying, actually, it's a very good investment because we've got a guaranteed discovery ahead of us. And we're exploring new terrain, which is what science has to do.
And actually, that's my question, leading on from that, is why do we need a new collider when we already have a collider?
So any collider, the question is tied in part with E equals mc squared. And what you're trying to explore is a certain mass range. M is the mass. And to get to a certain mass, you need a certain energy. And when you have a collider, it's limited in its energy reach. So you build it to go up to a certain energy and it can't go beyond. And you collect data at that for a while, for a couple of decades. But at some point, collecting more data doesn't get you much further. And the only way you can get further and explore really a new domain is to increase the energy. And that's where you need a new collider.
Right. Sabine, can I bring you in on that point?
Well, that's entirely correct. Yeah, I mean, so the problem is, if you want to build a collider that pushes more energy into those particle collisions so you can create heavier particles, at the moment, the way that it works is that it has to be bigger. And since those collisions create a lot of radiation that you just don't want people to run into, they put those colliders into underground tunnels. And it's really, really expensive to dig such a long tunnel and then put all those magnets in that have to be cooled with liquid helium and so on. So it's really expensive. And I think that's a factor we should not neglect. Now, Gavin says if you stop exploring the high energy frontier, you basically stop doing science. I think that's a little harsh. There are other things you could do to explore the foundations of physics. And I just think that this bigger collider is a little too much money for the little output that it's guaranteed to create. So yes, it's correct, there is some output there. It's pretty much guaranteed to create. It'll tell us more about the Higgs boson and some other particles. But when it comes to those big questions that I think people get inspired by, there's no such guarantee. There isn't even, a particularly good motivation for it, whereas we have those motivations for other experiments. So that's what I think we should do first.
I mean, to use Bjorn's vocabulary, should we be changing the narrative rather than looking at it in the way we've always looked at theoretical physics? Do we do something radically different?
Well, I think we should think a little bit more strategically. So in the past, a lot of breakthroughs have happened accidentally. It was just something that people saw popping up in their experiments. And this has driven a lot of progress historically in physics. Now, the issue is that if you have machines that are the size of, a ring of 100 kilometers or something, you don't discover things accidentally with a machine that size. You have to think very carefully about whether we're going to invest, like $40 billion or whatever the thing is going to cost. You don't just play around with those things. So you have to think very carefully about what kind of experiment is the most promising one to do with the money that we have, because we can't do all that we want. And so personally, I'd say, let's do something else first, see what we find, and then let's go back and think about building a bigger collider when we know a little more, and also when maybe the technology has progressed further so that the thing is not that hugely expensive.
And what kind of direction would you advise going into? Because, for example, with traditional computers, it's very logical, binary, and it's radically different to start researching something like quantum computing. Like, are you suggesting a radically different approach to physics?
No. So people ask me this all the time, and I always give the same answer, which is like, why are you asking me? So I think you should be, drawing in intelligence from all physicists about what can be done in their area, what they think the chances are. Use some intelligent approach to the question. The issue is, if you go and ask particle physicists if they want a bigger collider, they're going to say yes. So that's not a particularly good approach. Now, I could tell you what I would personally do, but this would just be my own personal interest. So
I want to hear it.
I don't think that's the right approach either. You want to hear?
Yes.
So I think we know that there's something wrong with the standard model in that it doesn't include gravity. So I think we should be doing more experiments to probe the quantum gravitational range. And I think it's possible to do this in laboratories. So I've been working on this for some while. There are a few small experiments on that, and they're making slow progress, but there's more that could be done. And there's also, in the area of quantum information, quantum computing, there's more stuff that could be done by the way of fundamental research that's not getting done. It's very strong in the technology range at the moment, but for what the fundamental research is done, I think there could be more being done.
Gavin.
So the question of what's important is a subjective one. So why do I think what particle physicists do is important? And why do I think the Higgs is worth studying more? Well, to give you an idea.
To continue watching this video, click the link in the top left or in the description below.
With a free trial, you can enjoy the full talk and thousands more.
Thank you for being part of the conversation.